This deadly question came to my mind yesterday. What if we took all the atoms in your body and removed the empty space? Well, you wouldn't feel much smaller, mostly because you'll be dead. The physical transformation of the universe will be significant. The atom is a massive lie. While microscopic objects feel solid, they are actually composed of vast internal voids. A typical atom has a diameter 10 to the power minus 10 meters, but its nucleus is roughly 10,000 to 100,000 times smaller. If an atom were expanded to the size of a football stadium, the nucleus, which contains 99.9% of mass, will be a small marble with a free outline. The rest is empty space, populated by electronic wave function. Assume you hand away the Pauli Exclusion Principle, the quantum rule that prevents identical fermions from occupying the same state and generate the generated pressure that keep atom from collapsing. The results are immediately disastrous. The moment you remove the space, volume ceases to be a meaningful concept for human life, because volume scale is the cube of the radius, V equal to 4 by 3 pi r cube. The nucleus occupies less than 1/10 trillionth of the atom total volume. If you compress the entire human population of 8 billion people this way, their combined mass will fit into the volume of a single sugar cube. The sugar cube will weigh approximately 4.5 times 10 to the 11 kg. While you could theoretically carry the entire human race in your pocket, the sugar cube density of 2.3 times 10 to the 17 kg per meter cube means it will immediately exert more pressure than the earth crust can support. Ordinary matter is supported by chemical thermal forces, but compressed matter is supported by neutron degeneracy, or the strong force. Forcing electrons to occupy the same spatial coordinates as the nucleus trigger inverse beta decay or electron capture. Protons plus electrons means neutrons plus valence electron. This process neutralizes the electromagnetic repulsion that usually keep nuclei apart. The result is neutronium, matter with a density of a neutron star. The problem is that this state is only stable under the crushing gravity of stellar scalar mass. On Earth, there is no 1.4 to 3 solar mass gravity to keep the degeneracy pressure in the check. Without that containment, the compressed matter expands explosively. A single teaspoon of this material will release 10 to the power 27 joules of energy. For context, a trillion megaton nuclear bomb is roughly the energy equivalent, or the sun total energy out for several seconds, will be released in your living room. If the compressor didn't perfectly convert everything into neutrons, you will face a column explosion. Protons are positively charged and repel each other with extreme force without electrons shielding or stellar gravity. The packed nuclei will fly up at relativistic speed as electrostatic potential energy is converted into kinetic energy. Additionally, free neutrons are unstable. Outside of a nucleus or a degenerate environment, they decay into protons and electrons with a half-life of about 10 minutes. The rapid decay of a neutron in our sugar cube will provide a secondary source of catastrophic energy release, vaporizing the surrounding atmosphere instantly. Now, you might worry that compressing a human to this density will create a black hole. Actually, it wouldn't. The source cell radius Rs for a 70 kg human is Rs equal to 2 gm by C2, approximately 1.04 into 10 to the power minus 25 meters. It is many orders of magnitude smaller than an atomic nucleus. You wouldn't need to compress the same human mass into space, 10 to the power 10 times smaller than a single proton to get an event horizon. However, for large masses, the threshold is reached quickly, with mass from physical radius and constant density scales with the cube rule. A sphere of nuclear matter becomes a black hole at approximately 3 solar masses. So here it is.